Chapter 10 here is about energy, types of energy. We're going to talk about how to calculate energy, something known as specific heat. We'll talk about as well in this chapter, and let's get into it here. So first off, a lot of times when we talk about energy and heat, it's really the type of part of chemistry that we often deal with, which is sometimes what is referred to as sort of thermodynamics. And thermodynamics will cover a couple of different things. It will really cover heat and energy. Later on in later chemistry classes, we'll talk about thermodynamics, and they'll talk about the idea of whether or not a reaction is sort of spontaneous or non-spontaneous. So that's a big part of sort of thermodynamics. Really, thermodynamics covers the idea of, whether or not, for example, a reaction will take place. So oftentimes what we deal with is a couple of things when we talk about energy, and especially sort of energy transferring from one place to the next. One part is what is known as the system. And the system is really the part of the universe we're interested in. So for example, if we're doing some type of experiment in a test tube, the test tube would be our system. Outside of the system, pretty much everything else is oftentimes considered the surroundings. So again, test tube sort of your system. Outside of the test tube, for example, would be the surroundings. When we talk about systems, there's a few different types of systems that we commonly deal with. One's an open system where you can have exchange of both mass and energy with the surroundings, which is a lot of times what we deal with. We also have a closed system, which allows transfer of energy, but not mass. So it's kind of closed off. You put a stopper on it. And then we can have an isolated system where there's really kind of no transfer of either their mass or energy. So a lot of times either an open system or a closed sort of system are kind of the systems that we deal with a lot in chemistry. Here's sort of an example of that open system, again, like a flask or something like that, where obviously mass could go in and out through the top. We can also have the exchange of heat with the system and the surroundings. Obviously, by putting like a stopper in there, that's going to prevent us taking out the mass from inside, but it's still going to allow that kind of exchange of heat that's going to occur. And then in an isolated system, everything's pretty much contained within, really no transfer of anything happening there. When we talk about energy, there are different types of energy. Energy is really the capacity to do work and produce some type of change. There is chemical energy, and that's the energy that's stored within the structural units of substances. There's also obviously energy associated, for example, within bond making and bond breaking. So a lot of what happens in chemistry is either we make bonds or break bonds, and in a chemical reaction or a chemical change, that's essentially what's happening. You pretty much got to break all the bonds on the reactant side and make all the bonds on the other side. So the process of making and breaking bonds also require energy sort of output or input. Making bonds. So if we were to make some bonds, we actually have to release energy. And if you think about it, you got two things that are sort of have a lot of energy. As they release energy, they're able to kind of slow down and kind of come together to make the bond. When we actually have a bond that we want to break, for example, you actually have to put energy in to do that. And if you think about that, you got a bond, when you put energy in, everybody gains enough energy and they can kind of wiggle away from each other in that sense and break it. There's also potential energy, which is the energy basically by the position of an object. The classic example is like the big giant boulder on top of the hill that's ready to fall off. That boulder possesses a certain amount of potential energy. When it actually does start to fall off, it will transfer to kinetic energy, which is the energy due to motion. The law of conservation of energy, which is really the first law of thermodynamics, says that basically energy cannot be created nor destroyed, but it can be transformed from one version to the next. So if you take sort of the example of the potential energy up there on the hill, it has a certain amount of potential energy. When it starts to drop, it gets some kinetic energy. And then when it hits and changes shape, apparently, it will actually come to rest at a new potential energy. All the energy that it had would then be transferred to hopefully no underneath, but the ground right when it hits. So it will transfer that energy to the ground when it does that. So when we think about energy, and a lot of times when we think about energy sort of in chemical reactions and what's going on, we do think of it as sort of a perfect sort of transfer of sort of energy in a lot of cases. So if somebody were to sort of release a certain amount of energy, there has to be somebody that will pretty much pick up the exact same amount of energy. So energy is oftentimes just transferred from one place to the next. And again, from like the system to the surroundings or from the surroundings to the system. The amount of energy that somebody loses is exactly equal to the amount of energy that basically somebody will gain in a process. Now, when we talk about energy, which is again, so really the study of thermodynamics, energy, along with things like pressure, volume, and temperature, they are what are referred to as being state functions. And what state functions are pretty much this. It doesn't really matter how you get there, what path you took to get there. What really is important in the look of state functions is pretty much two things: where you started and where you ended. So kind of like your final and your initial are really the most important thing. As we can see here, our blue hiker took the more direct route up the mountain. Our red hiker took the more scenic route around the mountain. At the end here, they both will possess the same potential energy because they're basically standing in the same location. They started in the same location. It doesn't really matter how they got there. And that's an important sort of idea for chemistry, because a lot of times we think about chemical reactions, for example, and we think about chemical reactions as always occurring, kind of like in a one-step sort of fashion. So we kind of think of it like, all right, A plus B, when it made E plus F, it just goes from one step to the next. And in chemistry, a lot of times that's not really the case. A lot of times there's a lot of little elementary sort of reactions or steps that occur along the way. So for example, what might happen in this case is, maybe A plus B makes C plus D, and then maybe C plus D react to make E plus F. And if we add these reactions together, anything on opposite sides of the arrow will cancel. So like the C's will cancel, the D's will cancel, and that will give us our overall reaction of what we're looking for. So in this particular case, maybe this does occur in a multiple sort of step process, which is what a lot of reactions really do. In terms of energy, it really doesn't matter. You just kind of add up all the energy needed to get there, and that gives you basically the energy that occurs. So that's a lot of times when we do something like we take delta E there, which is the change in energy, is final minus initial, delta P, which is the change in pressure, delta V, like we've done before, final volume minus initial volume, and delta T, final temperature minus initial temperature. So a lot of times what we look at really is sort of final and initial in these state functions. And when we talk about really a chemical reaction, we have our reactants that go to products in a chemical reaction. And you can think of products as like your final state and your reactants as your initial state. So a lot of ways that we calculate things like energy is to take basically products minus reactants, because in a chemical reaction, products is where you end up and reactants is where you started. So the difference in energy between those two is how we calculate it. Any questions on that there? So there are some important units for energy, and some of these you do need to know. So let's talk a little bit about some of these things. First off, really common units of energy are joules and kilojoules. So these are very common ways that energy is displayed as joules or kilojoules. That conversion is the same as any other kilo conversion. That is 1,000 joules is equal to 1 kilojoule. So that is a conversion, again, you should know, and obviously is used a lot. And again, it's the same as like kilograms to grams and all that good stuff. A relationship that we don't necessarily see a lot of in this class, but you do say in 1A, is that 1 joule is a kilogram meter squared second squared. So I will say probably not so much in this class that we'll see those units sort of pop up, but later on as you go through the rest of your chemistry classes, that joule and that relationship is an important relationship to understand. The other common units for energy are actually calories, and these are lowercase calories. A calorie is the amount of energy that's required basically to raise 1 gram of water by 1 degree Celsius. So a calorie and also a kilocalorie are two other common units of energy that come across. And once again, that relationship is the same as above. There would be 1,000 calories is 1 kilocalorie. The relationship between calories and joules is really an important one, and that's what's right there. 1 calorie is 4.184 joules. So those numbers, you do need to know that relationship. By the way, none of these are negative. That's just from PowerPoint, by the way. None of these are negative. So 1 calorie is 4.184 joules. The reason I emphasize that it is a lowercase calorie because we also will sometimes come across another common unit of energy, which is a capital calorie, if you will, capital C. And that is sometimes referred to as a nutritional calorie. And that actually is 1,000 of the little guys are 1 kilocalorie. So 1 kilocalorie is a nutritional calorie used with food and obviously exercise and stuff like that. So that equals 1,000 of the little calories, which is 1 kilocalorie. So one way that we use energy is to change the temperature of a substance, ice to liquid water. Obviously, as we heat it, we're supplying energy, and that's going to change the temperature as the water will gain a lot more energy. We see that reflection of the change in energy through temperature, right? Temperature starts to go up, right? And vice versa, if you put everything on ice, that'll be like removing energy. You would see the thermometer and the temperature start to drop down. So you definitely should know joules and kilojoules relationship, little calories and kilocalories, and the relationship between a calorie and a joule, which is a 4.184 number there. Now, when we talk about thermal energy, it's a little bit different than sort of temperature. Thermal energy is the energy associated with the random motion of atoms and molecules. Really, the more atoms and molecules you have, the more motion you will have, and that will actually result in a greater thermal energy. And that is a little bit different than temperature. Temperature is sort of a reflection of the energy that is being absorbed or given off. So if we had, for example, a cup of coffee that was at 70 degrees Celsius, has a higher temperature than a bathtub of 40 degrees Celsius, but the bathtub has much more thermal energy because obviously there's a lot more molecules in a bathtub than a cup of coffee. Therefore, water molecules would have more molecular motion and actually have more thermal energy, even though overall the temperature is less. It is less because a bathtub is much bigger, right? So even though it has a lot more energy going on, you need a lot more energy to the temperature of it, as opposed to a coffee cup, which is a very smaller amount of substance. Not as much energy is needed to see a bigger temperature change. So again, temperature is a reflection of the energy being absorbed or given off, but it is different than thermal energy. So if somebody talks about thermal energy, they are talking about really the motion and the amount of molecules that are there. Yes, sir.
Frankly, the thermal energy of something is basically just kinetic energy of molecules in ground. Right?
That is right. So it's based on how much molecules you have, and obviously the more molecules you have, the more thermal energy you would have, as they would be moving around, obviously a lot more. But there is a difference, obviously, in sort of how that is reflected in terms of the temperature. Heat is defined as really the flow of energy due to a temperature difference. Heat flows from cold to hot, hot to cold. Which way does it go? Goes from hot to cold, right? So the sort of warmer guy, right, will give off its energy to the cooler guy. It will absorb that energy, and the guy with the, say, lower temperature, for example, will probably rise. Guy with the higher temperature will come down, and they will sort of meet in the middle if they're in an isolated container. There are really two major types of processes that we talk about when we are talking about energy. One is an exothermic process. In an exothermic process, heat and energy is basically released. So heat and energy is being given off. So any process where we are releasing that energy, for example, to the surroundings, is a exothermic process. Very easy example there is striking a match, right? Or even lighting a Bunsen burner, right? You could feel the heat and energy being given off, obviously, to the surroundings when you do that. An endothermic process is any process where heat and energy is basically being absorbed. So a process where somebody picks up heat and energy is a endothermic process. So for example, if you had an ice cube, and even if you didn't do anything to the ice cube would pick up the heat and energy from the surroundings. And as it picks up the heat and energy from the surroundings, the ice cube will start to melt, right? As we all experienced that probably. So that is an endothermic process in terms of the ice cube. It would also be a exothermic process for the surroundings, right? It's giving off the energy to the ice cube, right? The ice cube is picking it up. So endothermic for one, exothermic for the other. So this also does tie into what we were talking about earlier with the law of sort of conservation of energy and that sort of transfer of energy. If you look at sort of both ends of the spectrum when this is happening, you know, there's always going to be somebody that will be absorbing energy, which is an endothermic process for them. But really, for them to absorb that energy, there has to be somebody else that's going to be giving off the energy, which would be exothermic for the other sort of party that's involved. That's the sort of the system surrounding energy moving from one place to the next. Another important thing, as we will go through this and we'll talk about, for the most part, there's kind of two types of energy values that we commonly come across in this class. One is referred to as Q, which is heat or energy, or delta H, which is the enthalpy. And we're going to talk about both of these a little bit later on as well. And these are very common sort of values that we perhaps might calculate along the way or maybe given to you along the way. And if you have a Q value or a delta H value, which is the, again, enthalpy, and it is a negative value, that usually implies that that process is a exothermic process. So whenever you calculate energy, you will either usually end up with a positive or negative number. And the actual sign that you end up with will tell you what is happening in terms of the energy. So if you calculate something there and it ends up negative in terms of energy, that usually implies an exothermic process. And opposite would be true for our opposite guy here. If you calculate a Q or delta H and you ended up with a positive number, that is usually a endothermic process. So especially when we calculate heat and energy, and we're going to talk about how to calculate Q here in this chapter later on. We always want to make sure that we don't ignore the sign that we get when we calculate energy. The sign is really important, whether it's a positive number or negative number when you calculate energy, because it does tell you sort of what is happening here in terms of exothermic or endothermic. Are two what are referred to as energy diagrams, and energy diagrams are used to sort of display what is happening in a particular reaction in terms of energy. So one is an exothermic diagram and one is a endothermic diagram. So let's take a look first off at the exothermic diagram on the left. This energy diagram shows us the energy of our reactants and the energy of our products. So remember, when we do a chemical reaction, we start with reactants, then we go to products. The reactants, again, are the starting materials in a chemical reaction. The products are what are obviously formed as a result of the chemical reaction. Whenever you see an energy diagram such as this, and you see that the energy of the reactants are higher than the energy of the products, a very simple way to look at it is, in terms of energy, the only way for those reactants to get down to the products is energy has to be given off. And that is why this is a exothermic reaction. The net result here is we end up with products that are lower in energy than the reactants where they started. So in terms of energy, that had to be given off in this process as this reaction took place. And that is opposite of our endothermic process here. The energy of our reactants are down here. Energy of our products are higher in energy than the reactants. So the opposite is true. In order to get our reactants sort of to that higher energy level in our products, energy has to be put in or absorbed in this case. And that is why we do see our products are higher in energy. So when you look at an energy diagram like that, that is really the way you can determine what type of reaction you're looking at. 100% of the time, reactants higher than products in terms of energy. Exothermic, opposite is true. If reactants are lower in energy than products, it is a endothermic process. When a reaction takes place, pretty much nothing happens, more happens here than we break all these bonds on this side and we make all the bonds on this side. Everything involves electrons, involves breaking and making bonds. That's the only process that occurs as you go from reactants to products. As you continue through this energy diagram, that process starts to happen. So I'll just draw maybe another one here. So we'll say these are our reactants, these are our products. So as the reactants start going towards the product side there, and they're working their way sort of up this hill, what is happening is they're starting to break all the bonds that they have, and they're actually starting to make new bonds as they progress through this process. And they eventually will hit really the very top of the hill here. And this is what is sometimes referred to as a transition state. And they will actually make something up here, just kind of call it an X. And this is what is sometimes referred to as the transition state complex, or sometimes referred to as the activated complex. And it pretty much is the peak in terms of energy. And one really important thing in chemistry is the idea of energy and stability. Are things in high energy really stable, or would they be less stable, you think? they would actually be less stable, kind of like our life, right? We don't want to be high energy all the time. We want to be low energy and relaxed is the most stable sort of way. And it's the same thing here. So anything that's really, really high in energy is not really a favored sort of situation. In fact, most things that occur in chemistry, reactions, breaking bonds, making bonds, all those things are all done in an effort to get to a kind of lower, more stable situation in terms of energy. So when we're at the very top here in this transition state and we have that transition state complex, that is really something where we have a species that is kind of have partially broken bonds and have partially made bonds. So it's sort of transitioning from reactants to products. And it's very, very unstable because it's really your peak of energy up there. And usually what would happen is relatively quickly, this guy will drop down to sort of the other side to make products. It's usually a lot of times very hard and to isolate that transition state complex because of that is like super high in energy, is very unstable. It doesn't hang around a very, very long time, and it will really go to the other side. Now, there is another sort of barrier to a reaction taking place in terms of energy, and it is this part right here. It is the part where we have the energy of our reactants to really the top of the hill. And that is what is known as E of A, or the activation energy. The activation energy is the minimum amount of energy needed for a reaction to take place. So activation energy, again, that minimum amount of energy that is required for a reaction to take place. For a reaction to take place where we will form products, there's really a couple of things that need to happen. There needs to be a collision, so things need to like hit each other, and they actually need to hit each other with the correct amount of energy. I guess there's a third thing to that. They actually need to hit each other in the correct location. So there's sort of like an active site, if you will, on both things. They got to kind of hit each other in the right orientation with the right amount of energy to actually form products. Not all collisions meet that. Not all collisions meet, I hit you in the right spot or I hit you with the right amount of energy. So just simply having two things run into each other doesn't necessarily mean that you are going to make products. They have to have this minimum amount of energy, and they also need to hit each other in the right space. You could think of the activation energy as essentially the hill that the reactants has to climb basically to get to the other side to make products. The activation energy has a really big effect on the rate of a reaction, how fast a reaction will take place. If my activation energy is really large, a really big hill, it is most likely going to take me a lot longer to get to the other side, and that reaction would most likely be a little bit slower than if you had a much smaller activation energy and you could get to the other side. It also means if you have a lower activation energy, there's probably a greater amount of molecules to actually have enough energy to hop over and get to the other side of that hill. When you have a much larger activation hill, you know, there's a lower amount of guys that probably have sufficient energy to get to the other side. So, you know, like if you were walking a hill, you had a nice small hill, you go up and over pretty easy. If you saw the big giant mountain, you know, not a lot of people are going to go up and over to the other side. So it's going to affect those things. We also see a difference here in the activation energy. This is again the activation energy here for our exothermic reaction, and down here to the top for our endothermic reaction. Which one is larger? It is the endothermic reaction, which also makes sense since that's a kind of a big hill. It's probably going to require energy be put in to help people get up and over the hill to the other side, as opposed to our exothermic one, where it's a much smaller hill. They have sort of excess energy. A good amount is going to be able to get up to the other side. So you typically will always see a bigger activation energy hill in an endothermic process, because that's basically why you kind of need that energy kind of put into reactions overall to sort of help everybody get to the other side. Any questions about there?
I know that it changes the energy that you add to something, it actually changes the products that are both reaction.
Cool, I like it. Other questions? Okay, so another important, we look at an energy diagram, and as we'll talk a little bit about in this chapter here, is the energy difference that we have actually between the reactants and the products here. This difference here is what is referred to as the delta H of the reaction, and that one, once again, is our enthalpy, or the change in enthalpy. That is basically the heat of a reaction. So one way that we very commonly calculate the delta H for a reaction is to take products minus reactants. So one way that we could calculate the delta H of a reaction is to take the delta H of the products minus the delta H of the reactants. Once again here, state function, as we talked about earlier, product final state minus reactants initial state. So final minus initial happening here. And although we don't really have numbers here, we could just imagine when we look at the energy of our products, it will be a larger number or smaller number than the energy of the reactants. So if this was like a scale, this would say it was like 2, right? Then we'll go 3 and then 4, right? So say our products is at 2, right? Lower energy than our reactants, which started at 4, right? So if I took something like that, 2 minus 4, I end up with what type of number? I end up with a negative number here, right? So if we made up some numbers here, say that was 2, that was 4. If I take 2 minus 4, I end up with a negative 2. We'll call it kilojoules. But important here is I end up, as I mentioned earlier, with a negative value for delta H, and negative values are associated with a exothermic reaction. So that is, how you would do that. And that would be opposite if we looked at our endothermic sort of process here. Let's quickly sketch a endothermic move. So once again, reactants, products, and we'll just call this 2 in this case. We'll come this way, we'll call that 4. Once again, here from here to here, this would be our activation energy. And the difference between here and here would be our delta H of our reaction. Once again, products minus reactants here. So if we did that, our delta H of our reaction, delta H of our products minus the delta H of our reactants. With my made up numbers here, my products would be 4 minus my reactants, which would be 2, gives me a positive 2, say, kilojoules. Again, a positive number here tells us is a endothermic process, which is what we see here on this particular graph. Any questions on that there? So again, these graphs here are what are sometimes referred to as energy diagrams. Any questions on any of that there? So you do need to be able to recognize an energy diagram. You need to be able to recognize it as being either an exothermic or endothermic diagram. You need to be able to understand what the activation energy is and where it is there. Any questions on it? So here's another sort of energy diagram. Once again, here, these are our reactants, H2O2 making water. These reactants were higher in energy than our products. So again, energy has to be given off from the reaction, the system to the surroundings, making it exothermic. Opposite here, decomposition of mercury 2 oxide, reactant to product. Products end up again being higher in energy, and that energy difference between the reactants and the products going to actually absorb energy in this case to get it up there. So a couple other things to finish up here, talking about exothermic and endothermic and sort of how we consider some of these things. An example of an exothermic reaction is this one here. That is methane plus some oxygen, CO2 and water. That's a combustion reaction. That's pretty much what happens when you light your Bunsen burner. And it gives off, in this case, 213 kilocalories of energy. When we talk about an exothermic reaction, although not perfectly correct in all aspects, we oftentimes will think of energy like this as being a product. So we sometimes will think of an exothermic process as it's releasing the energy. Is sometimes considered like a product, bless you. And that is opposite here than an endothermic reaction, where if we take some hydrogen, some iodine, add some energy, we get some hydriodic iodide there. And once again, we think of any type of process that's endothermic as the energy being a reactant, which is on the left-hand side of the arrow. So this is going to be important a little later on, really later on, very last chapter, we'll talk about it. But when we talk about what is known as Le Chatelier's principle, we think about energy and how it affects the reaction. And you oftentimes will think of an exothermic process as the energy being a product, while you think of an endothermic as being a reactant. Occasionally, they may write into the equation, like we see here, the energy value on the product side or the reactant side, which once again will tell you if it's exothermic or endothermic. In most cases, this is how typically a reaction is usually displayed to you in terms of energy. At the end, they'll just write delta H equals like a negative value, some type of number. So a lot of times they'll just give you the equation, and at the end of it, they'll say the delta H for this reaction is negative 300 kilojoules. And again, the number is not really important. It's the negative part that's important. As soon as you see the negative, you'll know it's exothermic. Or they may say in this reaction, the delta H is, positive 300 kilojoules. Again, the positive would tell you that it is endothermic. Any question? Yeah, so the delta H here is the delta H of, in most cases, the reaction. And it's really the idea of the change in energy of basically all the energy of the products minus all the energy of the reactants. So basically the difference between where you started and where you ended, basically. And they usually will give that as the overall delta H value for the reaction. Other questions? We'll talk about, I think, next time as well, but there's actually tables of like delta H values for all kinds of different substances that you can actually look it up. And that's how mathematically, if you were to say, or just given this equation, and they say, hey, calculate the delta H, you would go to a table, you would find the delta H value for CO2, you'd find the delta H value for H2O, you would add them together, then subtract it from the values you would find on the other side from that particular table. Any questions on that there? Okay, we will lay it up there today.